There was only one of them, a single locomotive built once, tested once, and never duplicated. No fleet, no sister units, no production run. Just one machine that walked into a Pennsylvania Railroad testing facility in 1946, produced numbers that no other locomotive in American history had matched, and then vanished so completely that most railroad historians spent decades assuming the records had been mislabeled. The Norfolk and Western Class A. Not the famous J, not the Y6B, the A machine that the railroad's own engineers described in internal memos as the most efficient steam locomotive ever operated in regular American freight service. If the numbers were real, and the Pennsylvania Railroad's independent dynamometer records confirm that they were, then the question is not why the Class A failed. It never failed. The question is why a railroad would build the most efficient freight locomotive in the country, prove it in controlled tests, run it profitably for over a decade, and then choose never to build another one. The answer cuts to the core of how American industry makes decisions, and why the machines history remembers are rarely the ones history should. The Norfolk and Western Railway occupied a specific and almost singular position in American railroading. Where Union Pacific moved general freight across thousands of miles of western mountain and plain, the Norfolk and Western existed to move coal. Appalachian coal, extracted from the seams of Virginia and West Virginia and moved by the millions of tons to tidewater ports and Midwestern industrial centers. The railroad's entire operational identity was built around this purpose. Its locomotives were designed for coal service. Its shops were built to maintain locomotives in coal service. Its engineering department spent its institutional energy on a single question repeated across every decade of its existence. How do you move more coal with less fuel, fewer crew changes, and lower maintenance costs per ton mile than any competitor? This was not an abstract engineering challenge. It was a survival question. The Norfolk and Western competed with truck, with barge, and with rival railroads for the same coal contracts. Every fraction of a cent saved per ton mile was a fraction of a cent that could be passed to a shipper as a lower rate or kept as margin. The railroad that solved the efficiency equation most completely would dominate Appalachian coal movement. The railroad that failed to solve it would lose contracts, then revenue, then eventually the capacity to maintain its physical plant. In this environment, locomotive design was not a prestige exercise, it was an existential one. The Class A emerged from this pressure in 1936, designed by the Norfolk and Western's own engineering staff under the direction of Chief Mechanical Engineer Robert Carmines. This detail matters. The Class A was not a machine ordered from a catalog, modified from a standard builder's template, or purchased from the American Locomotive Company or Baldwin Locomotive Works with minor customization. It was conceived, drawn, specified, and refined by engineers who worked for the railroad that would operate it, in shops that the railroad owned, using institutional knowledge accumulated over decades of running steam in the specific conditions of the Appalachian coal fields. The difference between a locomotive designed by a manufacturer trying to sell units across multiple customers and a locomotive designed by an operator trying to solve one specific problem is a difference that shows up immediately in the performance data. Manufacturers optimize for broad applicability. Operators optimize for the work. The Class A's wheel arrangement was 2-6-6-4. A configuration that balanced the competing demands of Appalachian service with a precision that no general-purpose design could match. 6 driving wheels on each engine unit provided the adhesion weight necessary to start and move heavy coal trains on ruling grades without slipping. The 4-wheel trailing truck supported a firebox of exceptional size, covering 182 square feet of grate area, fed by a mechanical stoker capable of delivering coal at rates that would have exhausted any human fireman within minutes. The boiler operated at 300 pounds per square inch, the same pressure as the big boy, but the steam distribution system that carried that pressure to the cylinders had been refined through years of operational experience into something that the Pennsylvania Railroad's test engineers, examining the Class A at Altoona in 1946, described in their official report as the most efficient steam cycle they had evaluated in the facility's history. The cylinders, each measuring 24 inches in diameter by 30 inches in stroke, translated that steam to motion with a thermal efficiency that the test records put at 12.2%, a figure that sounds modest until it is placed in context. The average American steam locomotive of the period converted between 6 and 8% of its fuel's energy into useful work at the drawbar. The Class A was converting 12.2%. It was, by the hard measurement of Altoona's independent instrumentation, roughly twice as thermally efficient as the industry standard. The test runs at Altoona in May and June of 1946 followed the Pennsylvania Railroad's established protocol exactly. Dynamometer car coupled directly behind the locomotive, standardized consist of loaded hoppers, weights checked and logged independently, calibrated drawbar scales, speed recorders, and pressure gauges producing continuous strip charts throughout each run. The test track level, the conditions documented in detail, weather, coal quality, crew composition, everything that could introduce variance recorded in the margin of each session's log. What the instruments recorded across 11 days of testing placed the Class A in a category by itself. The drawbar horsepower peaked at 5,500 at 35 miles per hour, lower than the big boy's 6,290, lower than the Chesapeake and Ohio Allegheny's 7,498. But the Class A was not being tested for peak output. It was being tested for efficiency, and efficiency is measured not at the moment of maximum effort, but across the full range of operating conditions that define actual service. At 25 miles per hour, the speed at which Appalachian coal drags actually moved on ruling grades, the Class A's thermal efficiency exceeded every other locomotive in the test facility's recorded history. The coal burned per 1,000 gross ton miles, the metric that translated directly into operating cost, came in at figures that the Pennsylvania's test panel annotated with the word remarkable in 3 separate places in the official log. Class A number 1239 was assigned to coal service on the Pocahontas Division in the autumn of 1936 and did not leave revenue service for 17 consecutive years. The maintenance records accumulated during that period, preserved in the Norfolk and Western collection at the Virginia Museum of Transportation in Roanoke, tell a story that the railroad's annual reports never publicized. Between 1938 and 1952, number 1239 required no unscheduled shop visits for mechanical failure. Scheduled overhauls came at intervals that Norfolk and Western's mechanical department superintendent described in a 1944 internal report as unprecedented for a compound articulated locomotive in heavy freight service. Crews who worked the Pocahontas Division in the 1940s described the Class A in terms that mixed professional admiration with something closer to disbelief. One engineer who logged more than 200,000 miles on Class A power between 1940 and 1953 recalled that the locomotive never surprised you. You asked it for something and it gave it to you. Every time. The same way. In July and in January. On a dry rail and on a wet one. It simply worked. And it worked at a level of consistency that made every other machine he had operated feel provisional by comparison. The Norfolk and Western built 43 Class A locomotives between 1936 and 1950, 43 units across 14 years of production for a railroad that operated hundreds of locomotives in total. The number is not large. It's not the 251 units of the British 9F, not the fleet scale of the Erie Railroad's triplex experiments, not even the 25 units of the Big Boy. 43 locomotives, each one built in the railroad's own shops, each one refined incrementally through the accumulated operational experience of the units that preceded it. The last Class A completed in 1950 was measurably more efficient than the first completed in 1936, not because the fundamental design had changed, but because 14 years of running the machines in actual service had revealed exactly where the design's tolerances could be tightened and where they needed relief. This kind of iterative refinement, manufacturer-independent and rooted in operational reality, was something that only a railroad building its own locomotives could achieve. It was also something that would end the moment the railroad stopped building locomotives, which it did in 1953 when the board authorized the diesel conversion program. The decision was not made because the Class A was failing. The maintenance records available to the board in 1953 showed that the Class A fleet was performing better than it had in any previous year. The decision was made because the diesel conversion program offered something the Class A could not, a future in which the railroad no longer needed a locomotive manufacturing facility in Roanoke, no longer needed the specialized workforce that operated it, and no longer carried the capital exposure of building and maintaining a fleet of machines that no other railroad in the country operated, and for which no commercial parts supply network existed. The Class A's greatest operational strength, that it had been designed specifically for Norfolk and Western service and built in Norfolk and Western shops, was its fatal institutional weakness. It existed entirely within the boundaries of one railroad's organizational capacity. When that capacity was redirected, the machine had nowhere else to go. The last Class A was retired in 1959. Not one was preserved. The Roanoke shops that built them were converted to diesel maintenance facilities. The engineering drawings were archived and then, in a series of document disposals that the railroad's historical records describe only in passing, partially destroyed. The men who had designed, built, and maintained these machines retired or transferred to other assignments. The institutional knowledge that produced the most efficient freight steam locomotive dispersed into silence over the course of a decade, leaving behind 43 scrap records and an Altoona test report that sat in a Pennsylvania Railroad archive box for 30 years before a graduate student researching an unrelated topic opened it and found the word "remarkable" written 3 times in the margins.